In this lesson, we are going to look at finishing up our conversation about nonlinear inequalities, and specifically we're going to look at 3 examples from homework 4. We're looking at problem 9 from homework 4, problem 16, and problem 17. We'll do them in order of appearance, so 9 first, then 16, then 17. And what you'll notice is that even though it's the very first one in the list, number 9 is the most involved. So let's kind of dig in and see what we find. Looking here, you'll notice that this inequality is not set to 0 on one side. You have 1 plus 2 over x plus 1 on the left and 2 over x on the right. I want to remind you of this from what we talked a little bit about in our previous lesson. So we don't want to multiply both sides of this inequality by x over x plus 1. And the reason for this is we don't know for any given value of x times x plus 1, is it positive or is it negative? And of course, you remember inequalities have a pretty important reaction to being multiplied by negatives on both sides. With a variable expression, it's going to be positive some of the time and negative some of the time. So it's really not good practice to multiply both sides of an inequality by a variable quantity, because if you do, you have to account for when it's positive, when it's negative, and it actually turns into a lot of work. So rather than multiplying both sides by anything, what we're going to do first is we're going to, and you'll notice I'm going to space it out really generously. We're going to subtract 2 over x from both sides. And once we have that, we have 1 plus 2 over x plus 1 minus 2 over x is less than or equal to 0. And now we're going to put everything over the common denominator. The good news is that the 2 denominators in question here are not, they don't share any factors. They're what we call relatively prime. So the common denominator is just going to be x times x plus 1. So the rest of this putting things over a common denominator process is just asking, okay, what does it have and what does it still need? So for example, 2 over x already has an x, so it needs an x plus 1. So we're going to multiply by x plus 1 top and bottom. 2 over x plus 1 has an x plus 1, but it doesn't have the x, so we're going to multiply top and bottom by x. And then 1 doesn't have a visible denominator. So if you wanted to write its denominator, you could. It would just be the number 1. So in order for it to go over the common denominator, we need to multiply it by both on the top and on the bottom. Okay, so let's go ahead and do this, right? So by design, this is going to lead to us having the denominator x over x plus 1. Here, with the 1, there's nothing to distribute. We just have x times x plus 1. In fact, let me go ahead and distribute that so that we don't spend an extra step. So we have x squared plus x plus 2x. And now here, watch out, the negative 2 is going to distribute all the way through the x plus 1. So it'll be negative 2 times x, which is minus 2x, and negative 2 times 1, which is minus 2. Combining like terms in the numerator, we'll end up with x squared plus x minus 2 all over x times x plus 1. And in this case, you'll notice that x squared plus x minus 2 factors. So that's what we're going to do. What I highly recommend is pause the video right now, try factoring it on your own, and then start the video back up again to see if you were able to factor it completely. All right, let's start back up again. So we have x squared plus x minus 2. That factors into x plus 2 times x minus 1 over x times x plus 1. So now that this is all cleaned up, what do I mean by that? So the inequality no longer has this problem of not being set to 0 on one side. We've put everything over a common denominator, and once we did that, we combined like terms, we factored out, so that now we've got our entire expression decomposed into simple factors on the top and simple factors on the bottom. This allows us to see the critical numbers. It allows us to construct the sign chart quickly. Notice no non-negative factors here. There are no perfect squares, no even powers. It's just singletons. So what that tells us about our sign chart is that we're not going to have any critical numbers where the sign won't switch passing through. All right, so let's go ahead and start this process. So the critical numbers are -2, 1, 0, and -1. In keeping with our color coding system, let's make the sign chart purple. So remember, for critical numbers, we just put them in order. We don't really worry about scale so much. We just put the critical numbers in order. And again, we're not going to do the whole build-up sign chart process. We're going to pick a test point. You can pick anything you want to be your test point. I'm going to test -5. Why -5? Kind of no reason. It's convenient that it's in the leftmost region. That's going to make it a little more streamlined to construct the sign chart. But the test point can be anything that's not a critical number. So if you really wanted to use 7, you could. If you wanted to use -1/2, you could. Anything you want is fine. Just be really clear on which region it's in. Okay, so I'm going to plug -5 in for x for each one of the factors in our fully cleaned up form, and we'll see what we have. If you plug -5 in for x, you see that x plus 2 is negative. So is x minus 1. So is x. So is x minus 1. Oh, well, negative times negative is positive. So we have positive on top divided by positive on the bottom. So that means the expression is positive over that whole region. Now remember, no non-negative factors, which means that the sign changes as we go through each critical number. And you'll hear me refer to that as a flip-flop sign chart. So there is my sign chart. Okay, now what did we want? We wanted to know, where is this expression less than or equal to 0? And as we've said many times before, less than or equal to 0 means negative or equal to 0. So where do we see negative on our sign chart? We see it here. We see it here. So that's negative. What about equal to 0? Well, this is where it's really important to pay attention with rational expressions, because division by 0 is absolutely undefined. So it's okay for the numerator of a rational expression to be 0. That happens at -2. And it also happens at 1. So we include those two endpoints. However, it's not okay for x plus 1 to be 0. So we do not include the -1. And it's also not okay for x to be 0, so we do not include the 0. Notice that our solution is broken up into two disjoint pieces. So we're going to use the union symbol in our solution set. So writing the solution set up here in the little box, we'll go from -2 to -1, not including the -1, but including the -2, and then from 0 to 1, not including the 0, but including the 1. In WebAssign, remember, it's also going to ask you to graph the solution on the number line. I'm not going to do that for this problem because it's fairly self-explanatory, but for number 16, we'll actually take a second and hop over to WebAssign, and I'll walk you through the process of constructing that graph, just because it might be a little confusing. The beautiful thing about number 16 is that everything is already given to us cleaned up. Everything is factored, we can see all of the pieces, we can dive straight into identifying the critical numbers and plotting the sign chart. Okay, so let's do it. Critical numbers. This might be a good moment to pause the video and say, okay, let me see if I can find the critical numbers on my own. So try doing that and then come back once you have them to check. All right, looking at the critical numbers, we're going to ask when is 2x minus 1, 0? Where is x minus 7, 0? Where is x minus 9, 0? So our critical numbers are a half, 7, and 9. Before we move on, I hope this is something that all of you have noticed right from the beginning and that all of you have been sitting on the edge of your seats waiting for me to point it out. We have a square here. X minus 7 squared is a non-negative factor. So no matter what x is, x minus 7 squared will not be negative. So this is very significant for our sign chart because it means that there will not be a change in sign around the critical number 7. Okay, I think we're ready to make the sign chart. Remember, we're always going left to right. So 1/2 is the leftmost number, then 7, then 9. Notice again, I'm not paying attention to scale, I'm just paying attention to position. Test value, test point. Let's use 0. 0 is a favorite of mine. Plus, it's in the leftmost region. It's just a really great example here. Okay, here we go. If x is 0, 2x minus 1 is negative. If x is 0, x minus 7 is negative, but then we go to square it and it becomes positive. And then if x is 0, x minus 9 is negative. So on top you have negative times positive, which is negative. On the bottom you have negative. Negative divided by negative is positive. So that means the leftmost region is positive. To make sure we don't lose focus, let's one more time remind ourselves that the 7 is a big, big deal here because 7 is a critical number that came from a non-negative factor. So there will be a change in sign around the 1/2. It was positive to the left of a half, but it's negative to the right of a half. However, there is no change in sign around the 7. So it's still negative on the other side of the 7. There is a change in sign around the 9. So they put a plus over that region. Okay, what did this problem want from us? Again, it came pre-cleaned up, so that's nice. We wanted to know when is this expression negative. Notice that this is a strict inequality. So strictly less than 0. So this is where I'm negative. And this is where I'm negative. But I'm not negative at 7. If x is 7, I'm equal to 0. Again, if that doesn't make sense, if like you need a second to chew on that, pause the video, plug 7 in for x and see what happens. So how do we indicate that we need to skip the 7? Well, we've discussed this already in our previous lesson, but we're going to exclude it. One way to do it, and the way that I do in my lessons, is to put these sort of back-to-back parentheses, indicating that we skip over the 7. But I'm going to show you in WebAssign in just a second how we do it, because you can't put back-to-back parentheses in WebAssign. Okay, so how do we write this in interval notation? So we take the interval from 1/2 to 7, skipping both the 1/2 and the 7, and then the interval from 7 to 9, skipping both the 7 and the 9. In case you're feeling the urge or wondering, wait, well, skipping to 7 does not just mean you're starting at 8. Remember, we've talked about this before. Intervals consist of real numbers. So like 7.1 is totally allowed. 7.01 is allowed. Any number between 7 and 8, there's infinitely many of them really, is allowed into the solution set. It's just 7 itself that's not included. So that is the process of solving number 16. Let's go into the homework in WebAssign. Here is number 16. And what do we have here? So our solution set was what? Now I'm forgetting. So from 1/2 to 7 and from 7 to 9. So this is a great problem to do in WebAssign because, first of all, how do you indicate 1/2? So it's not a precision game, right? From 0 to 1, 1 is about there. So 1/2 is going to be about in the middle between 0 and 1. So you don't need to be super, super careful. Now, look, I'll show you something, and then we will, and then we'll kind of undo it. So if I wanted to put the 7 here, right? So I'm putting a parenthesis at the 7. What I cannot do is I can't put an open parenthesis there too, right? It has to be like a little ways away. It can't be on the, well, maybe it can be. I wonder, you can try this. Last time I taught this class, it wouldn't allow this. It wouldn't accept it. So try it. See what happens. But I believe WebAssign won't accept it. So there. Again, you can try this. And you can see if WebAssign will accept it. So notice, of course, I have to shade the intervals between the 1/2 and the 7. So if WebAssign doesn't accept it, which I don't think it does, we can erase and put an empty circle, an open circle on the 7. So the open circle means skip that value, and then we take everything from 1/2 to 7, so shading up to the empty circle, and then everything from 7 to 9, so shading everything after the circle. So again, I do not believe WebAssign will accept back-to-back parentheses like that. I believe that the way WebAssign will accept the solution to this problem is to use the empty circle to indicate that you're skipping the 7. But try it both ways and see what happens. Report back. Okay, back we go. So now looking at number 17. So number 17 is a question I often get when we're doing this class face-to-face, so I thought that I would sort of anticipate some of the questions, maybe even not finish it all the way, but at least get the setup going. So one of the first things you notice about number 17 is that it's not set to 0 on one side. Gotta fix that. So we start by subtracting x to the 6th from both sides. Now we need to get to a point where we can see the critical numbers. So how are we going to do that? Again, you might pause the video, think about what you might do here, and then come back. The way we're going to approach this problem is we're going to realize, wait a minute, x to the 8th and x to the 6th have a factor in common. I can factor x to the 6th out. And what I get left over is x squared minus 1. From here, it's very handy to notice that x squared minus 1 factors further. Into x minus 1 times x plus 1. Okay? And so now we're mostly ready to dive in, but I want to point out x to the 6th is an even power. And as we talked about before, if you take any real number and raise it to an even power, regardless if that even power is 2 or 4 or 6 or 44, any number raised to an even power will be positive. So the critical number that comes from that factor is going to be one of those where there won't be a change in the sign. Again, if you want, you could challenge yourself to see if you can identify the critical numbers. Pause the video and restart it in a couple of seconds. The critical numbers here, looking factor by factor. X to the 6th is 0 when x is 0. X minus 1 is 0 at 1. X plus 1 is 0 at negative 1. So we have 3 critical numbers here, and one of them came from a non-negative factor, namely 0. So when we go to draw the sign chart, so again, put your critical numbers in order. And you pick a test point. You can put anything you want that's not critical. So, I don't know, let's test negative 3. Look what happens. Negative 3 to the 6th power. Any real number to an even power is positive. So that's positive. And then x minus 1 is negative when you plug in negative 3. And so is x plus 1. Okay, so we have positive times negative is negative, times another negative is positive again. Now look, 0 came from a non-negative factor. So there will not be a change of sign around the 0, but there will be a change of sign around everything else. So we have a positive to the left of negative 1. We will have a change in sign as we pass through negative 1. So this changes to negative. And we will still have a negative on the other side of 0. Because there is no change in sign as we pass through 0, since 0 came from a non-negative factor. Last but not least, there is a change in sign as we pass through 1. So that becomes a plus. Going back to our inequality, what was it asking us? It was asking us, when is this expression greater than 0? Which is strictly positive. So that's those tail ends. Everything that's to the left of negative 1 and everything that's to the right of positive 1. Since it's a strict inequality, we don't even think about it. We exclude both of the endpoints. Once again, our solution set is made up of 2 disjoint components. You'll notice that happens quite frequently. And let's write it here in interval notation. We have negative infinity to negative 1, union 1 to infinity. So that is 3 very different lessons from homework number 4. And I hope that between the different problems that we've done for homework 4 and the other examples that I made up myself, you now have a really solid understanding of how sign charts work, how we use them to solve nonlinear inequalities. We will use sign charts nonstop in this class. We won't just use them to solve nonlinear inequalities. So I highly recommend, if you ever find yourself feeling, wow, I am getting rusty on my sign charts, go back and review these videos. I will do micro reviews when we come to this sort of thing again, when we need sign charts again, but this is really going to be the meat of that conversation. So this concludes our conversation on sign charts, and this is the last lesson for week number 2. See you soon. Bye.